Hi students, good morning. Welcome to physics class. How are you doing? I really miss you all in the real classroom. I hope that we will meet in the real classroom very soon. Pray well students. In the physics class, we have started the third unit, that is laws of motion. In this, you have listened introduction and Newton's laws. Newton's first law, Newton's second law, and Newton's third law. Isn't it? State Newton's first law. Newton's first law states that every object continues to be in the state of rest or of uniform motion unless there is an external force acting on it. Newton's second law, the force acting on an object is equal to the rate of change of momentum acting on the object. That is F equal to dp by dt. In that, you have learned 1 Newton. Define 1 Newton. 1 Newton is defined as the force which acts on 1 kilogram of mass to give an acceleration of 1 meter second raised to minus 2 in the direction of force. Newton's third law, for every action there is equal and opposite reaction. You have learned some examples of these three laws also, isn't it? Let's move on to today's session. Today's topic is discussion on Newton's laws. The first point, Newton's laws are vector laws. Newton's laws are vector laws. That is, F vector equal to ma vector, where F is the force, is a vector quantity, m is the mass, is a scalar quantity, a is the acceleration, it is a vector quantity. In Cartesian coordinate, this equation can be written as fx I cap plus fyj cap plus fzk cap is equal to max I cap plus mayj cap plus mazk cap. By comparing on both sides, the three scalar equations can be written as fx equal to max, fy equal to may, fz is equal to maz. So fx is equal to max, fy equal to may, and fz is equal to maz. Fx is equal to max. When the force is acting along the x direction, acceleration also along the x direction. When the force is acting along y direction, acceleration is also along the y direction. When the force is along the z direction, acceleration also along the z direction. So from these equations, we can understand that the force acting along y direction cannot alter the acceleration along x direction or z direction. Force acting along x direction cannot alter the acceleration along y direction or z direction. Okay? Similarly, force acting along z direction cannot alter the acceleration along x and y direction. This is the first point. The second point is the acceleration experienced by the body at time t depends on the force which acts on the body at that instant of time. The acceleration experienced by the body at time t depends on the force which acts on the body at that instant of time. That is, f of t is equal to ma of t. That means acceleration of the object does not depend on the previous history of the force. Acceleration of the object does not depend on the previous history of the force. It depends only on the time of force, that particular time of force. For example, in the cricket match, when the bowler bowls or when the bowler throws the ball to the batsman, once the ball leaves on the hand of the bowler, it undergoes gravitational force and the air frictional force. Once the ball leaves the hands of the bowler, it experiences only the gravitational force and the air frictional force. So the acceleration of the ball here, it is independent of how the ball was bowled. The acceleration of the ball is independent of how the ball was bowled. So acceleration of the ball or acceleration of the object does not depend on the previous history of the force. Understand? The next point. The direction of the force and the direction of motion. Sometimes the direction of the force and the direction of motion are in the same direction. Sometimes may not be in the same direction. So direction of force may be different from the direction of motion. Let's see the special cases for this point. Case 1. Force and motion in the same direction. Force and motion in the same direction. Consider an apple falling from the tree. So this is tree. An apple falling towards the earth. Here, the direction of the motion of the apple is downward. That is, this is the direction of the velocity of the apple. Also, the force, gravitational force. Gravitational force acting towards the earth, that also acting downward. So the velocity is acting downward, gravitational force also acting downward. Here the force and the motion are in the same direction. Case 2. Force and motion not in the same direction. Force and motion not in the same direction. For example, moon orbiting in elliptical orbit around the earth. Moon orbiting in elliptical orbit around the earth. So consider this is earth and this is moon. So this moon is revolving around the earth in an elliptical orbit. We know that there is a force acting towards the center of the elliptical orbit. So this force is known as centripetal force. Centripetal force that is acting towards the earth. But when you consider the direction of motion of the moon, at this point the direction can be mentioned by means of drawing a tangential line. So this is the direction of motion and this is the direction of the force. So here force and motion are not in the same direction. Force and motion are not in the same direction. Force is acting in this towards the center and direction of motion of the moon is acting away it is. in this elliptical orbit. The next case is force and motion in opposite direction. Force and motion in opposite direction. When a man throws a ball, so if an object is thrown vertically upwards, the direction of the motion is acting upward, isn't it? This is the direction of the motion of the object. But the gravitational force acting downward. Gravitational force is acting downward. Here, the force and the motion are in opposite direction. This is the gravitational force. And this is the motion of an object. So motion of an object is upward. The direction of motion is upward, but the gravitational force is acting downward. Case 4. Zero net force, but there is motion. Zero net force, but there is motion. Consider the raindrop. That is this raindrop coming from the cloud. So raindrop coming from the cloud, and it experiences two forces. One force is gravitational force, that is acting downward. Another force is upward air drag force. Upward air drag force. There are two forces acting on the raindrop when it comes from the cloud to reaches the surface of the earth. That is gravitational force and air drag force. The gravitational force is acting downward and the air drag force is acting upward. First, this is the upward force, that is air drag force, and this is the gravitational force, gravity. When it descends slowly, the upward air drag force increases. So this is the raindrop, and the upward air drag force is increases and cancels with the gravity. Here I have drawn a small length arrow. Here it is big magnitude. And when it descends down, the raindrop descends down, this air drag forces increases and it cancels with the downward gravity. So from this we can understand there is zero net force. This upward force and this downward force get cancelled, equal and opposite. So there is zero net force is acting on it. But this raindrop moves with a constant velocity. Moves with a constant velocity. Hence a raindrop comes with a zero net force, therefore with a zero acceleration, but with the non-zero terminal velocity. This is case 4. That is zero net force, but there is motion. Okay. For example, raindrop coming from the cloud, it experiences two forces, gravitational forces and upward air drag force. At first, the air drag force is less comparatively gravitational force. When it descends, the air drag forces increases, and at a particular time, it cancels with the gravitational force. So there is zero net force is acting on it. Also, this raindrop moves with a constant velocity. So we can say the raindrop comes with a zero net force, therefore the zero acceleration, but with a non-zero velocity. The next discussion is, if multiple forces F1, F2, etc. Fn act on the same body, then the total force, the net force, is equivalent to the vectorial sum of the individual forces. What's that? If multiple forces F1, F2, etc. Fn act on the same body, then the total force, that is net force, is equivalent to the vectorial sum of the individual forces. That is, F net force is equal to F1 vector plus F2 vector plus F3 vector plus etc. Fn vector. That is F net. F net is equal to ma vector. Already I said Newton's laws are vector laws. So it should obey the vector additions. For example, the forces acting at particular angle. Consider this is one force and another one force. This is A vector, this is B vector. So what is a resultant vector? According to the triangle law of addition, the resultant vector is the closing side of the triangle. So this is the net force. Understand? Vector addition of forces, that is A plus B, gives the resultant C. Example, bow and arrow. That is two forces. One is acting this direction, another one is acting this direction. Bow and arrow example means we can consider this is the string forces. This is the string forces. When the two string forces are acting in this direction, the arrow is going along this direction. So this is the net force direction. Net force direction. F1 and F2 are the two forces acting along the string. This is bow and arrow. So the arrow passing along the net force direction, that is in this direction. Here the direction of acceleration is in the direction of net force. The next discussion is, according to Newton's second law, F vector is equal to ma vector. A vector is equal to d square r vector by dt square, where A vector is known as the acceleration. Isn't it? Acceleration is the second derivative of position vector of the body. This already we have discussed. Acceleration is the first derivative of velocity, but second derivative d square r by dt square. So we can say second derivative of position vector of the body. From that expression, we can say Newton's second law is basically a second order differential equation. Second order differential equation, and whenever the second derivative of position vector is not zero, that is d square r by dt square is not equal to 0. Whenever the second derivative of position vector is not 0, there must be a force acting on it, acting on the body. So Newton's second law is basically second order differential equation, and whenever the second derivative of position vector is not 0, there must be a force acting on the body. The next discussion is, if no net force acts on the body, then m dv vector by dt is equal to 0. That is, no net force in the sense f vector is equal to 0. F vector is equal to 0 means ma vector is equal to 0. That is, m into dv vector by dt is equal to 0. If no net force acts on the body, then m dv vector by dt is equal to 0. Whenever there is a differential concept of one quantity is equal to 0, that quantity is considered as constant. Differentiation of one quantity is equal to 0 means that quantity is considered as constant, or else when we are differentiating a constant, we will get 0. Accordingly, we can write m dv by dv vector by dt is equal to 0 means v vector is equal to constant. V vector is equal to constant. Here, m dv vector by dt is equal to 0 is Newton's second law. And v vector equal to constant is Newton's first law. That is, Newton's second law, the force acting on the body is directly proportional to the rate of change of momentum. So here m dv vector by dt is equal to 0. And v vector equal to constant. That implies the first law, that is every object continues to be in the state of rest or of uniform motion unless an external force is acting on it. Isn't it? So second law is consistent with the first law. Second law is consistent with the first law. But Newton's first and second laws are independent laws. They can internally consistent with each other but not derived from each other. The next one is Newton's second law is cause and effect relation. Newton's second law is cause and effect relation. Here force is the cause. Force is the cause and acceleration is the effect. Okay? Conventionally, the effect should be written on the left side of the equation and cause should be written on the right side of the equation. Effect should be left side and cause should be right side of the equation. So the correct way of writing Newton's second law is ma vector equal to f vector instead of f vector equal to ma vector. The correct way of writing Newton's second law is ma vector equal to f vector, or else dp vector by dt is equal to f vector. dp vector by dt is equal to f vector. Students, so far we have discussed the Newton's laws. First point we have discussed Newton's laws are vector laws. In the second point we have discussed the acceleration at a particular time depends on the force acting on that time. And third we have discussed the force and motion or in different directions or same directions. Force and motion in the same direction, force and motion not in the same direction, force and motion in the opposite direction, also zero net force but there is motion. Then if multiple forces are acting on the same body, what is the total force? That is equal to the vector addition. And we have discussed that the acceleration is the second derivative of the position vector. So whenever the second derivative of position vector is not zero, there must be a force. Next, Newton's second law is consistent with the first law. If m dv vector by dt is equal to 0, we can write v vector is equal to constant. And last, Newton's second law is cause and effect relation. So force, cause and acceleration is the effect. So effect should be written on the left side of the equation, cause should be written on the right side of the equation. The correct way of writing Newton's second law is dp vector by dt is equal to f vector. The next topic is application of Newton's laws. In that, first, free body diagram. Free body diagram. What is meant by free body diagram? It is a simple tool to analyze the motion of the object using Newton's laws. Free body diagram is a simple tool to analyze the motion of the object using Newton's laws. To draw the free body diagram, we have to follow some steps. First point, identify the forces acting on the object. Identify the forces acting on the object. Second point, represent the object as a point. Represent the object as a point. Third point, draw the vectors representing the forces acting on the object. Draw the vectors representing the forces acting on the object. So, three steps. Identify the forces acting on the object. Represent the object as a point. Draw the vectors representing the forces acting on the object. Here, one more important point. Forces exerted by the object should not be included in the free body diagram. Forces exerted by the object on the object can be included, but forces exerted by the object should not be included in the free body diagram. So what is meant by free body diagram? It is a simple tool to analyze the motion of the object using Newton's laws. And there are some steps to follow the free body diagram. Identify the forces acting on the object, represent the object as a point, draw the vectors representing the forces acting on the object. And here, the forces exerted by the object should not be included in the free body diagram. When we are doing some problems, we can understand the free body diagram. Let's see the example 3.1. A book of mass m is at rest on the table. A book of mass m is at rest on the table. What are the forces acting on the book? First question is, what are the forces acting on the book? Second question, what are the forces exerted by the book? Third one, draw the free body diagram for the book. Draw the free body diagram for the book. Let's see the solution. This is the table. A book is rest on the table. Okay. First question, what are the forces acting on the book? We know that there are two forces acting on the book. One is gravitational force, another one is normal force. One is gravitational force, another one is normal force. That is, gravitational force is acting downwards. Gravitational force, normally we can write m into g, which is acting downwards on the book. Which is acting downwards on the book. Second force is normal contact force or normal force. Normal contact force, we can denote as N, which is exerted by the surface of the table on the book. Normal force is exerted by the surface of the table on the book. It acts upwards. It acts upwards. This is the first question answer. Second question is, what are the forces exerted by the book? What are the forces exerted by the book? Actually, there are two reaction forces are exerted by the force. Two reaction forces are exerted by the book. One is, the book exerts an equal and opposite force on the earth which acts upwards. The book exerts an equal and opposite force which is mg acts on the earth which acts upwards. So gravitational force is acting downward, in that the reaction force is acting upward. That is, the book exerts an equal and opposite force mg. Equal and opposite force of gravitational force. That is mg on the earth which acts upwards. Second reaction force. The book exerts a force which is equal and opposite to the normal force. The book exerts an equal and opposite to the force. That is opposite to the normal force on the surface of the table which is acting downwards. So these are the two reaction forces. Then third question. Third question is, draw the free body diagram. How to draw? So first step is identify the forces. We have identified gravitational forces and normal force. Second step is represents the object as a point. So here the book is a object. So we can represent as a point. Third one, draw the vectors representing the forces acting on the object. So this is the book, the vectors. This is normal force and this is gravitational force. So this is the free body diagram. Free body diagram. I think you all got that first problem. Next problem, example 3.9. Apply Newton's law for an object at rest on Earth and analyze the result. Apply Newton's law for an object at rest on Earth and analyze the result. Let's draw a figure. This is an object, maybe ball or anything. This is rest on the Earth. This is Earth's surface. This is rest on the Earth. So obviously we know there is a gravity. Gravitational force mg is acting downward and normal force which is acting upward. Gravity acting downwards, normal force acting upward. Here the inertial coordinate system we can consider like this. This is an x-axis, this is an y-axis. So this is the positive y-axis, this is the negative y-axis. So we can say the gravity acting downward in the negative y direction. Gravity is acting downward, so we can say it is in the negative y direction. Normal force is acting upward, which is in the positive y direction. Let's draw the free body diagram. How to draw the free body diagram? So there is an object. Identify the forces. We have identified gravitational force. So we can draw a vector mg and normal force n acting upward. Here we can write the equation such as F net to force. How can we calculate the F net to force? First we can write the gravitational force, F gravity. G is equal to minus mg j cap. Why this is minus sign? Because gravity is acting downward, that is in the negative y direction. So we can write minus mg j cap. And normal force, that is n vector, that can be written as n into j cap. This is acting positive y direction. Okay, so what is F net to force? Fg plus n. F net to force can be written as Fg vector plus n vector. That means F net force is equal to, what is Fg? Minus mg j cap plus n j cap. Here the object is at rest on the Earth's surface, so there is no acceleration. Acceleration is equal to 0. So by applying Newton's second law, F is equal to ma. F is equal to ma vector. Here the a vector is equal to 0. So we can write F net vector is equal to 0, or else we can write minus mg j cap plus n j cap, that is equal to 0, or minus mg plus n into j cap is equal to 0. By comparing the components only, we can write minus mg plus n is equal to 0, or else we can write n is equal to mg. N is equal to mg. So in the question, they are asked to analyze the result. Here we can conclude that when the object is at rest, the magnitude of normal force is exactly equal to the magnitude of gravity. When the object is at rest, the magnitude of normal force is exactly equal to the magnitude of gravity. Students, I hope that you have understood this problem. Try to do some problems such as 3.2, 3.3, 3.10 and 3.11. So these problems, try it in the note. So today we have seen discussion on Newton's laws and free body diagram. So learn these two questions and solve the problems. Thank you, students.